We have a really small pack.
Good morning, everybody. How are we doing today?
Happy.
So for those of you that got here a little bit early, I was playing some music for you. Why? Yeah. Right, we're going to be studying music today and sound and where it comes from. But you know, I wanted to, we'll get back into that. We'll get back into the.
I have a suggestion.
What's that?
Have you heard of the Deep Listening album?
Yes.
Great album.
Yeah, it's okay. But I needed it to be really orchestral, right? For reasons that you'll see here in a second. All right, I left you. I kind of was rushing the Doppler effect, and it's okay. The math isn't that hard. It's that just make sure that you use the equation I gave you towards and away, get your signs right, you'll be good. I want to talk about now what happens when you push the Doppler effect too far. What's this? That's breaking the sound barrier. Okay, so this is what happens to air when a plane transitions from subsonic to supersonic. It forms this shock wave, and the shock wave is a pressure wave that in this case causes condensation of the water vapor that's in the air. And so we can actually visualize and see that shock wave forming. You'll notice there's a big one coming off more or less the trailing edge of the wing. But do you see the tiny one coming off of the cockpit? Okay? There's actually more than one sonic boom that comes off of an airplane. But usually the plane is too short for our ears to be able to hear the distinct booms. It's like, it's boom, boom, but it's like they're right on top of each other, and we can't just, in time, we can't separate out the two booms. The Concorde, when it used to fly, the only supersonic airliner that's ever flown, it was long enough that you could hear the double boom. Okay, you can hear the boom coming off the front and the boom coming off the back of the plane. So let's talk about where these booms come from. I did not make this animation. I'm not responsible for the shade and hate thrown at both Microsoft and Apple in this animation, but I thought it was funny anyway. Okay, so a sonic boom occurs whenever an object is flying faster than the speed of sound. So airplanes can do this, right? They can fly faster than the speed of sound. So they can go faster than the 343 meters per second. And what you get is, so like Doppler effect is that effect where in the front of the object that's moving, that's producing sound, the waves get squished together, and behind it they get spread out, and so that changes the frequency and wavelength. Here, the object is moving so fast that the center of the sound, the next wavefront that's made, is no longer inside, okay, all of those bubbles coming out. And so instead, what you get, can we go backwards, please? Thank you. Instead, what we get, do you see what's happening to all the wavefronts? They're all bunched up. And so if you're standing where the tree was or where the house was, as that plane flies over, what are you going to hear? You're going to hear nothing, 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 and then all of a sudden, all of the sound waves that that plane has been making will catch up with you simultaneously at that wavefront boundary where they're all piling up. After the plane goes by, you'll just hear the roar, Doppler shifted down. But prior to that, so a sonic boom is you hearing all of the waves at once, right? As they all catch up with you simultaneously. The angles that are made within this so-called Mach cone, Ernst Mach was a German physicist that studied supersonic, and so the Mach number is a multiple of the speed of sound. So if you're going Mach 1, that's the speed of sound. Mach 1.5 would be 1.5 times, so it's 343 times 1.5, right, so on and so forth. The angle of this Mach cone gets tighter and tighter the faster you go. So just as you break the sound barrier, it's kind of wide open, but as you get faster and faster and faster, the cone narrows down. Planes, of course, aren't the only things that can break the sound barrier. Bullets can, right? And here is a Schlieren photograph of the pressure waves that are forming at the front end and trailing edges of the bullet, and even some peeling off towards the middle. Okay? However, this picture, this cone shape that you're seeing here is actually something that you are probably seeing in real life, because it's not just sound waves that can form these cones. Any object that moves faster through a medium than waves can propagate through that medium will produce this shape. And it has a very specific name when it's applied to a very common occurrence. It's a wake. What's a wake? It's the combination of all the waves piling up on each other simultaneously as the boat moves through the water faster than water waves can move through the water. So it's not just sound, right? All I was going to do, and then in a boat, the faster it goes, the narrower the cone becomes, and then you throw a rope on the back of the boat and a board to somebody's feet, and they go wakeboarding, right? They are literally surfing, okay, on not a sonic boom, but the piling up of wavefronts as that source moves faster through the medium than the waves can move through the medium. Drive slower than that, and you'll just have ripples going out in front of the boat. And boat hulls are designed to be able to take advantage of this. They're shaped so that they're more efficient the faster they move through the water to a certain extent. But like a boat can be very inefficient if it's moving slower than the speed of water waves. But it can be very efficient. It can ride up higher, less friction, all that kind of stuff if it's moving faster. So there's lots of engineering that can take place. All right. Before we get into standing waves for pipes, I wanted to, I remembered to bring the demonstration. I forgot to do this in lab yesterday, right? So I apologize. What we got here is just an amplifier with some speakers, okay? And let's see if we can pull this off, because there's an effect that takes place when sources of sound are combined, that constructive and destructive interference that I told you about. So I want to try and see if we can't do some destructive so you can kind of hear. You're not going to hear completely destructive, because that's really hard to do in this room. So let's see if we can't pull this off a little bit. What I'm going to do is I'm going to use this to generate a tone. It's going to be annoying. It's going to be 440 hertz tones. It's just going to be a constant source of sound. But that's what we need in order for this thing to work properly. And as I play this, I'm just going to play the tone from my phone. As I play this, I'm going to need you to kind of move your head side to side, actually by about a meter, so don't knock the person next to you. Okay. You can also, if you need to stand up, you can walk up and down the row. Okay. You can go forward or backward, or you can kind of go side to side, right? But what you're going to listen for is a change in the volume of the tone. So let me just make sure I'm connected. I am. And hear anything? So it's not working. That was did somebody mess with the buttons back there, darn it? Okay, let's make sure that the tone generator is working. Okay, there we go. I just want to see you guys go back to sleep. Do you hear the shift? Is it going wow, wow? And if you get your head, you can kind of maximize it, and then you can try and find the minimum, right? You're hearing the overlap of sound waves, right? The overlap, and as they overlap in such a way that they are canceling each other out, that's where the volume dies down. And then when it gets louder, what are the waves doing? They're both peaking at the same time. Okay? So if you got a peak and a trough together, it's a cancellation. You've got a peak and a peak, it gets louder. As you shifted your head in space, okay, you found where the minima were and where the maxima were.
What if you hear it really loud and like one
Yeah.
really quiet in the other?
It has, okay, so let's do that. Let's test your hearing. So, raise your hand if you can hear the sound. Here we go. So put your hands in the air. Everybody should be able to hear this one. Okay? Okay, broke. Oh, there we go. Oh, it won't let me slide. This is a dumb one. Who's ever get another one here? Yeah. Shut up. Calibration successful. All right, let's see. Let's do this one.
This one might be definitely.
Okay, everybody should be able to hear that. Okay. Just so put your hands up if you can still hear it. Okay, so a lot of you went, you have good hearing. I am not a doctor, okay, right, okay? But I drove this all the way up to 20,000 hertz, okay, sliding it up, okay? And most of you put your hands down around 19,000 hertz, okay? I couldn't hear it after 12,000. Okay? But I also had an explosive go off in my face. Okay? I was holding it in my hands right here. It was in the Philippines. During Christmas and New Year's, there's a lot of firecrackers that they use, and they're all homemade. Okay? And the firecracker I was holding was like half of an M80. I don't know if anybody's ever played with firecrackers. Like M80 is like a quarter stick of dynamite. This is a no nonsense thing, right? Okay. So what we were doing is we were lighting them and tossing them into a barrel, and then they would float. Okay. So I had the firecracker in my hand. I lit the fuse. Fuse was nice and long, but the fuse was faulty, and it went. Okay. And I saw it. All the firecrackers up to that point were just nice slow fuse, right? This one went, and it started moving. I knew instantly what was going on, and I just dropped it. I dropped the lighter, I dropped the fire, and it was right here when it went off, right? Blew off my clothes, right? Like burn marks on my skin, and I lost hearing for a half hour. Like I couldn't. I thought I had lost my hearing, full stop, right? But my hearing eventually came back, okay? And ever since, I have not been able to hear above 12,000 hertz.
Is that called a detonation cord? The ones that go all
Well, det cords are really fast stuff.
Yeah.
This was just called some idiot made this cord,
Right.
and I took the brunt of it. So yeah, watch out for homemade fireworks. So anyway, just giving you an idea of that superposition, that interference of waves, and then kind of a hearing test. I would go to the low part of the frequency spectrum, but these speakers aren't capable of going down to like 20 hertz. Right? So, not nearly as fun. All right. We're going to use standing waves and pipes, and then we're going to talk about music. We've figured out, well, we've done standing waves on strings, which is the part of the orchestra that's got all the violins and cellos and anything that's guitars, anything with strings on it. You need to understand something about pipes in physics. When we say the word pipe, we mean the kind of pipe you might go down and buy at the hardware store. PVC, metal, doesn't matter what it is, usually metal, right? But it's open on both ends. When you buy a pipe, typically it's open, right? You can look down the tube and you can see through it. So we call that an open pipe. When we say an open pipe or just pipe, we mean it's open at both ends. We use the word closed pipe. What's the first image you get when I say closed pipe? Closed on both ends? Okay, that's called a pipe bomb. Okay? A closed pipe in physics means it's closed at one end. One end is open, one end is... If you have it closed on both ends, then no sound can get out. Right? Now, are there situations where you have waves in a pipe and it's closed on both ends? The answer is yes. That's called your shower. Why do people sing in the shower? Because it sounds awesome? Okay. Because you hit resonant frequencies of the standing waves that exist in your shower, and that builds on your voice and makes your voice sound better and feel stronger. Okay? So your shower is a pipe closed on both ends, right? Which turns out to be exactly the same as a standing a wave on a string. But we need to do standing waves, which on a string, right, we have the transverse waves and they weren't going anywhere. But now with sound waves, we got to do longitudinal waves. So what does a standing wave look like? What does a wave look like in air?
It's like a compression.
It's a compression and a rarefaction. Remember I talked about this? And the air molecules are kind of doing this. So sending a pulse down a pipe means you have to have, at one end, you have to have a disturbance, right? You got to vibrate. You got to get the air molecules moving somehow, okay? And so in this case, it's a plunger. On a trumpet, it's a person's lips, right? On a saxophone, it's a reed, right? There's something that's causing a vibration, a wave to happen. Pushes the air, and then subsequent pushes end up with these traveling compressions down the pipe. The distance between those compressions would be the wavelength. But when it comes to a standing wave, right, how do we picture so I'm going to play this video, and they're going to create standing waves in a pipe. And they've got cork dust in the bottom so that you can see where the air is vibrating a lot and where it's vibrating little. So this is about the closest we can get to a real visualization of the air molecules. The way they're going to generate the wave, though, is very close to scraping fingernails on chalkboards. So just fair warning to you.
We'll use this long glass tube and some cork dust to demonstrate standing sound waves in a column of air. The standing waves will be produced by driving the air in the tube with the output from this rod. When the standing wave forms, the motion of the air pushes the cork dust into regularly spaced piles.
Antinodes, nodes. Antinodes, nodes. Right? Places where the air is moving a lot, places where the air isn't moving at all. Right? So that same node-antinode pattern exists in a wave in a pipe. Drawing it, though? How do you draw that? You pretend it's a transverse wave. Okay? That's what you do. So that's why you'll see pictures. Here's a pipe, open on both ends, right? And what do we draw? We don't draw compressions. We just draw transverse waves moving down the pipe. So we're going to fall back to the visualization and mathematics of a standing wave on a string. With a big wink, wink, we know this is a longitudinal wave, but mathematically it doesn't matter. We can visualize it as a transverse wave in the pipe. It's just easier to draw. It's easier to see where the nodes and antinodes are if you just draw the transverse wave. So, are we lying here? Well, yeah, we lie all the time in physics, right? No friction, doesn't matter, all this kind of stuff, right? But this is one case where the lie is just, it works just fine. Because it ends up being the same math anyway. So, different from a wave on a string, though. What were the boundary conditions for a wave on a string? What's on either end of that string? Nodes or antinodes? Nodes. It's two nodes, right? They're fixed. They're tied down over there. For an open pipe, a pipe open on both ends, the air is free to wiggle at those open ends. And so those, by definition, have to be antinodes. And so if you have a pipe that's open on both ends, and you know you have to have an antinode on one end and an antinode on the other, the standing wave pattern always has to be node, antinode, node, antinode, node, antinode, node. You can't do two antinodes next to each other. That's not a standing wave. And so what's the smallest, least pattern we can fit in this pipe if there's two antinodes on either end? Putting a node in between. And so an antinode's a peak, this node is an equilibrium, so the next antinode must be a trough. And how much of a wavelength is pictured in this pipe? Half. We're going from peak to trough. And in order for there to be a full wavelength, what do we need? Peak to peak, or trough to trough, or equilibrium to equilibrium, right? So this is half of a wavelength, which they're saying up there, right? The length of the pipe, I need 2 lengths of that pipe to fit a whole wavelength. The frequency, being just the speed of the wave divided by its wavelength, ends up as V over 2L. Where have you seen that before? It's the same equation as the one for a wave on a string. All right, let's do the next picture, which I know is on the screen, but let's produce it. We know it has to be antinodes on either end. Those are the boundary conditions. Now, if I'm going to put the next least pattern in here, what do I have to do?
Antinode in the middle.
I've got to put an antinode in the middle. Everything's got to be spaced out, and I'm going to have 2 nodes. Right? So I go from an antinode, which is a peak, node, which is an equilibrium. Next antinode's a trough, back to equilibrium to peak. How many wavelengths are there? That's 1 wavelength. We go from peak to peak on that thing. Okay? And so if the length of the pipe is L, then the wavelength is the length of the pipe. And our frequency of the second one ends up being twice the frequency of the first one. So let's look at the third one. There's the third harmonic on the screen, right? Again, the wavelength is 2/3 the length of the pipe. We get 3V over 2L. What's going on here? Our nth harmonic is still n times the fundamental. What's the fundamental? V over 2L. And what is n telling us? Ooh, is it the number of antinodes? It's the number of nodes. So for a wave on a string, n was telling us the number of, it was telling us the harmonic number, but that harmonic number correlated to the number of antinodes on that string. For a pipe, it's the number of nodes in the pipe. That's really the only thing that you need to conceptually change in your brain. Otherwise, n is just equal to some integer value, okay, for whichever harmonic number you happen to be on. So the good news is, math is the same. Concept, like, really close to the same. It's just, instead of counting antinodes, we'll count nodes. Not that big a deal. All right. Now, whenever I see this, I always want to do Batman.
No.
Or na 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 na.
Hey.
You guys.
Wait, I know it. What?
I know, I'm one person. Okay. Let's now shift to closed on one end. And I'll get to the actual musical instruments that look like this in a bit. Okay. But here, a pipe that's closed on one end has a different set of boundary conditions. The ends of the pipe are dictating to us what it can and can't do. So by way of derivation, so you can see the concept and how it ties in. We've got this closed end. The opened end is an antinode, so what's the closed end?
Node.
It's a node. And do we have to do anything for this fundamental pattern? Like, do I have to add a node or an antinode in there in order for this to be physically possible? No, I could go from an antinode to a node, right? But that's peak to equilibrium. How much of a wavelength is that? It's 1/4. So here we have a fundamental change, ooh, pun intended, to the pattern. Our fundamental frequency isn't going to be V over twice the length of the pipe. It's going to be V over 4 times the length of the pipe. And what's more, when we go to the next pattern, we keep the same boundary condition. But now, can I just drop an antinode in here? Remember, a standing wave has to be what? What's the pattern for a standing wave? Node, antinode, right? You can't have two antinodes together. You can't have two nodes together. So if I just drop a node in here, is this physically possible? No. Can I just drop an antinode in here? No. What am I forced to do? I have to add a node-antinode pair to the pattern. In order for the standing wave to exist in a pipe that's closed on one end, the next harmonic, peak to equilibrium to trough, back to equilibrium, is how much of a wavelength? 3/4. 3/4 of the wavelength is in the length of this pipe. And so when I go to solve for the frequency, and you can even see what they're doing with the numbers here, they did not call this the second wavelength. What did they call it? They called it the third. And the frequency of this one, if the frequency of the first one was V over 4L, the frequency of this third one is 3V over 4L. You want to guess what the next, well, you can see it on the screen. What's the next one going to be? 5V. What's the next one going to be? 7. What the heck is going on here? The value of n has to be what? Odd. It must be odd. So our fundamental is V over 4L. Our nth harmonic is still n times the fundamental, but n is odd only for the closed pipe. In other words, in a closed pipe, the even harmonics don't happen. They simply can't exist because of the boundary conditions of the system. An instrument that is closed on one end sounds very different from an instrument that's not. And I'll try and demonstrate that for you here in just a little bit. With video, not with my own personal playing of any instruments. Those of you that were worried. Okay, so the mistake you're going to make is when they give you a closed pipe, you'll use V over 2L. Don't do that. V over 2L is for what? Open pipe and waves, standing waves on a string. You have to change your equation when it's a closed pipe. It's V over 4L. How easy is that? A mistake is that to make? It's a factor of 2 and it's going to happen, right? Okay. And then, if you are given a problem where they said, this pipe makes a frequency and, only the odd ones are present, what do you instantly know? You know it's a closed pipe. Okay? So, be aware, right? It is odd only. In open pipes and on strings, your integer can be any value. But here. And this is where acoustics goes wrong again. Because there are textbooks and websites that will call this wavelength 2. They'll call this one the first harmonic of the fundamental. You see how I could go wrong really fast? Which is why we're trying to standardize on, use the number that matches the harmonic frequency of the math, and not some weird system of overtones or calling the second harmonic of the pipe, which is really the fifth resonance. And, oh my gosh, it goes south really fast when they start using different words for the same thing. Yeah. Blame the acoustical scientists on that. That is definitely their fault. So let's do some examples and then we'll do some demonstrations. Okay. So reading the problem, you want to key in on what kind of pipes you got. What kind of pipe is this? It's an open pipe. They're giving us information about an open pipe. So we know that the fundamental frequency of an open pipe is V over 2L, right? And we also know that that fundamental frequency is equal to 261.6 hertz. Okay. Then they tell us something else. And I did this one on purpose. I wanted you to see where the physics textbooks and websites and everything will try to mess you up. And the homework in our book is no exception. They do this too. They're saying the third resonance of a closed pipe. Again, they're trying to trick you. Is the third resonance of a closed organ pipe n equals 3, n equals 5, or n equals 7? The only way I knew what the correct answer was to look at the key. Because there are some systems where the fundamental is never referred to as a resonance. Where resonance refers to, you got a fundamental, and then you have the first resonance, which would be the n equals 3. And the second resonance would be the n equals, right? But in this particular, whatever grad student came up with the solution for this problem, they defined the fundamental as being a resonance, being the first resonance of the pipe. And so the third, it would be first, second resonance. So third resonance, the n number would be what? 5. Just take deep breaths. Okay? I'm not responsible for this. It's just, this happens, okay, in this subject, and we got to deal with it. On an exam, I will be very clear what I am talking about. I'll just give you harmonic. Like, I don't want to test this. This is dumb, okay? I just want to know, can you work your way through standing waves, right? So if you're not sure on the exam, you read it, I screw up, I forget to change the wording, whatever. Come on, Mr. Vale, I don't know, what resonance are you talking about here? I will tell you, right? Like, I won't sit there and go, right? Because this is a dumb game. It really is a stupid game. It's semantics, and semantics is English, and I don't like English. So here, this third resonance is the fifth harmonic, where the fundamental is the first, the third one would be the second resonance, so on and so forth. Okay. We know that this fifth resonance of the closed pipe, what is the fifth resonance of the closed pipe mathematically? 5V over 4L, good. Okay? We know that it has to be equal to 261.6 hertz. How do we find the lengths of these pipes? Basic algebra. L is going to be 261.6 divided by 2 times 343. How did I know what the speed of the wave was? It's in air, right? It's the speed of sound. And I got...
You just messed up.
what did I do wrong?
The 261 should be on the bottom.
I said it was basic algebra. And so therefore it went all wrong. I can do differential equation. That's going to be 343 divided by 2 times 261 points. There we go. It's because I put the numbers. I should have never put the numbers in right away. Always screws me up. I got 0.656. Is that what anybody else got? I can't read my writing, which is why I'm hedging on this one. About the same. I mean, it's in the ballpark of those numbers, so I'm going to go with it. What's that?
0.66.
Okay, 6. Yeah, fine, great. And then over here, let's solve this one. L is going to be equal to 5 times 343 all over 4 times 261.6. And there I got 1.64 meters. So easy to go wrong in the concept, apparently very easy to go wrong in the math because the math is too easy. But really, not. This isn't even approaching 4A hard, is it?
No.
Yeah. And some of you I know are looking at me wondering if you're actually in the right class. Right? Because physics is not supposed to be this easy. Easy to mess up. Still physics. Right? So let's do another example. All right, what do we got here? Okay. Oh, okay. So they're cutting this pipe, but they didn't say they cut it in half. In fact, I know that they did not cut it into the same, like it's not in half. There's one that's longer than the other. How do I know this? The frequencies are different, right? If they were the same length, the frequencies would be the same. So, we know the fundamentals of the two. As a matter of fact, which one's shorter?
The 256.
Longer the pipe, the lower the frequency. This number gets smaller. What happens to this number?
It's bigger.
It gets bigger. The higher the frequency, the shorter the pipe. A piccolo, a flute, a tuba. Only the tuba is all wound up in itself. Right? If you unstretch a tuba, it's really long. Right? So, yeah, length. Longer the length, the lower the note. Okay, so I know that this pipe was cut into two parts. Unequal parts. There's one part, there's another part. I know that this one is 256 hertz, and I know that this one is 440 hertz. They want to know the original fundamental frequency and the original length of the pipe. Well, these are both fundamental frequencies, aren't they? And without any other information, I'm going to assume that they are open pipes because nobody said they're capping them or anything, right? V over 2L. So solve that for L. That's V over 2 times 256. This one is V over 2 times 440. And when I do that, I got 0.67 meters and 0.39 meters. So what's the total length of this pipe? 1.06 meters. And now how do I find the fundamental frequency of this original pipe? The fundamental is going to be V over 2L, isn't it? Which is going to be 343 divided by 2 times 1.06. Then I get 162 hertz. Now, of course, on your homework, I've given you harder ones, right? These are all warm-ups. I think on your homework, like I gave you one where you got to like figure out the harmonic number. They give you two adjacent frequencies or something like that. You got to find the harmonic ratios that fit and stuff like that. Those tend to be a little bit more involved, but just because they're math puzzles, not necessarily physics puzzles. And so when you're getting stuck, be sure to ask your study buddies, things like that, tutors, me, something to get unstuck. All right. Can I go back? I mean, you guys can on YouTube and on the PDF, but I'll leave it up because I want to transition into talking about music now. So let's play a game. So we're gonna take all this physics that we learned about standing waves on strings, standing waves on pipe, and apply it to creating music. For those of you that are going to be upset that all of the examples I'm giving to you are coming from classical music, that's too bad. We can't talk about modern music with electronic instruments until you take physics 4B. Those of you in 4B, did I play you? I played just, yeah. So, because we did Faraday's law of electromagnetic induction, didn't we? Okay, let's do, name that tune. Okay, somebody knew what Howard Shore was. Let's see if you know this. Now, this comes from a piece of music that I will tell you about here in a second. But I'm going to fast forward this to the section that I think you're going to recognize. But probably for all the wrong reasons. Okay, let me find it. I got to search for it. I'll find it here. Okay, it's coming. It's coming. It's coming. That's not it. Where is it? Oh, here we go. Have you heard this before? Does it sound familiar? What's this from? Does anybody know this piece of music? What? Shrek? What is it? What is the music doing to your emotions? It sounds grand, doesn't it? Okay, it sounds full, it sounds majestic, maybe even heroic. Here's another one I'm going to have to go through. Changed, didn't it? Is this the music you hear as you walk towards the test?
As you pass it out.
Is that passing them out? What's the mood or emotion of this?
It's a minor keys.
Dark, right? Heavy, foreboding. I think somebody actually knew what this was. What piece of music was this? Thought I heard it out there. Did it sound like Star Wars?
Is this right?
Listen. Here it comes. Here it comes. You can tell it's coming, right?
Yeah.
Something's building. Here it comes. Wait for it. Wait for it. Did you hear it? No, you didn't. Because that was not John Williams. This is John Williams. And listen, wait for it. There it is. The same thing you just heard in that first piece of music, slowed down. But listen to what's going on in the background. It's the same rhythm, slowed down for the melody, as what's going on in the background, which is exactly equal to this. It's the same rhythm.
Is this just Mars?
What's this piece that I was playing before?
Mars from the planet.
Mars from the planets. Okay? Gustav Holst in 1906 or 8 wrote 8 pieces of music. Pluto had not been discovered, but that's okay. Pluto's not a planet anyway. Come fight me. Okay? I will win. Right? He wrote 8 pieces of music. All of these pieces of music were supposed to be representative of the planets. And by planets, Gustav Holst meant the Greco-Roman gods that the planets were named after. So Mars was the god of war. Okay? And with war comes that foreboding terror, right? So the piece of music was written to evoke that dread, right? And that foreboding aspect of war. The first piece I played for you, that I know you said comes from Shrek, because I actually played it in Shrek, okay? But I know you've heard before, very close to that theme, was from Jupiter. Now, who was Jupiter in the Greco-Roman pantheon?
Zeus.
He was Zeus, who was also king of the gods. Okay? And so the music is supposed to be majestic, kingly, heroic, right? This is the entrance of Zeus into Olympus, and so there's all this pomp and circumstance. So Gustav, and of course, this is the planets. I had to play it for you in physics class, right? It's like you don't have a choice, right? So those pieces of music that Holst wrote, he wrote, like I said, 8, but it's really Jupiter and Mars that are the most famous. When John Williams sat down and needed a piece of music that represented the foreboding evil of the galaxy, what did he borrow from? There was a theme already set to go.
He does that a lot.
He does it a lot. John Williams is one of the best composers of our age. He is our Bach and Mozart and all that sort of stuff.
Well, he's just a master of quotation. It's like
And he knows the musical language that music nerds are familiar with. If you've ever studied music, you know about Dies Irae. Dies Irae is a musical pattern that exists coming out of Gregorian Roman Catholic chants. If I played it for you, you'd go, oh yeah, I've heard that before, because you hear it everywhere. It's a melodic series that is just very familiar to anybody that's trained on Western music. John Williams does the same thing. And so when he needed Jaws, it was the beginning of Mars. It was that two-tone da-da that Mars had right at the beginning. When Howard Shore, and I was playing that, the Lord of the Rings soundtrack when people were coming in, when Howard Shore needed majestic music for Aragorn's theme or whatever's going on in the movie, he reached towards Jupiter. There's a reason that you hear a lot of French horns and trumpets when it's some heroic thing, right? And you hear a lot of sad violins. Violins are sad anyway. When you need something that's more moody. Like this. Okay, what instrument is that? That's the piano. There's the cello. It's a very famous piece of music called The Swan. Okay? It's from Camille Saint-Saëns' collection of musical pieces that was representative of a trip to the zoo. So you're watching the swans, and this is supposed to be a very lovely bird. Swan. What's this? What instrument's that? That's the flute. My wife's a flute player. This is not her recording. Okay? But I can't get this kind of thing in the house all the time. How did you know it was a flute? Heard it before? What it sounds like? Sounds different from the violins behind it, right? This is called the aviary. What is the flute supposed to be presenting to us? The birds, right? Fluttering around and doing their birdie thing. This is also from the Carnival of the Animals. What animal is that? Monkeys. Nope. Close. Anybody that's ever taken music lessons knows what these are. They're scales. So what animal is this? The pianist. Camille Saint-Saëns threw this in. The whole works, all the set of works in Carnival of the Animals was supposed to be fun musical exercises for his students. That's what they were for, right? And so the flute players got to do their thing, and the cellists got to do their thing. Well, he couldn't help himself. He threw in scales and said, this wasn't the birds, this wasn't the swans, these are the pianists, because they belong in the zoo. Anyway, people throw shade in every discipline. Did I get through? Okay. Here's a piece of music I know you've heard.
Let us know.
What instrument is it? Piano. Who wrote this piece of music? Ostensibly one of the most haunting melodies ever to be put down in classical music. And the most boring. It's just like, can we please pick it up? Like, come on! Right? So yes, it's beautiful. I had to play this way too often when I was doing my piano and organ studies. I've heard this song too many times, right? For me to be able to appreciate it anymore. There's better pieces of music out there, right? But I play all of those things for you. This is also Beethoven. This is Violin Romance number 2. You can tell the difference between that and 12, right? Those instruments sound different. Even though they're all playing the same notes. It's all the same Western, European musical scale based on 12 notes. And yet, you can tell the difference between the instruments. You may not always be able to name the instrument, but you can, I know that's a different instrument than that one. And you've had enough exposure, you go, that's a piano, that's a flute, that's a cello, that's a violin. I'm not responsible for the English spelling of this word because, well, it's probably a Latin word anyway, but the voice of a musical instrument, its characteristic sound and the way that you know what the instrument is called the timbre. Okay? The timbre of a musical instrument is its voice. The timbre of the piano is very different from the timbre of a flute. In fact, flutes are often called very pure sounding instruments, like the sound that they make is kind of closer to a sine wave or a pure tone than, say, the fullness and richness of a piano. I'm not trying to throw shades at flutes. My wife's a flautist, I gotta be careful, right? But there's just a richer body of sound that comes out of playing a note on the piano than playing the same note on a flute. And since we're already talking about it, how do you tune two piccolo players? Piccolos are the really short flutes that play really high notes. You probably heard, if you've heard any Sousa marches, patriotic marches.
You step on one of their foot.
You shoot one of them. That's the joke from my wife. Piccolos are notoriously difficult to tune. There's only one other instrument that's harder to tune than piccolo, and that's the oboe. You guys know that? Any oboe players in here? No? Okay, good. I make fun of them. Oboe players, their instrument is so hard to tune that they will... Has anybody ever been to a concert, like an orchestral concert? Okay, so there's all of this pomp and circumstance that's around, right? And so they warm up, right? If you get there early, they're probably like kind of warming up and doing all this kind of thing. And then before the conductor comes onto the stage, right? The first violinist will come out, okay? And she or he will stand there, and if they're doing it right, will take their bow of their instrument and they will point at the center of the orchestra. They are pointing at the oboist. Okay? The oboist will either stand up, usually stand up, and play an A above middle C, and the rest of the orchestra will tune to the oboist. That's how hard it is to tune an oboe. Let's let that person set the note for everybody. Okay? If they're doing it wrong, the first violinist will come out and play a note on their violin, and then everybody will tune. That's a total lie. They've already tuned to the oboe. You just weren't there to hear it. Okay? So yeah, there's all this pomp and circumstance and stuff that's surrounding it. And it's kind of dumb because there's this culture surrounding orchestral music, and it's kind of all snooty and that kind of thing. And people will get like shushed for clapping during the movements or stuff like that. And a bunch of conductors have come out lately going, why? That's like an old-fashioned thing. If you want to clap, clap. Like if you're happy about the piece of music that just happened, clap! Right? Like, come on, it's awesome. So anyway, we're trying to get the old snootiness out of the building. The other thing that's you need to know about orchestras is that in the United States we tune to 440 hertz as our A above middle C. In Europe they tune to 445. That's the way it is. That's why two different recordings will sound different to somebody that have perfect pitch. The other fun story about that is if you were to point out sort of any major performers in classical music that are very famous, or if performers are not your thing, brands of musical instruments that are considered normal or good or any of that kind of stuff. What sort of names come to the front? Oh, okay, but like current day. Yamaha, Suzuki, Steinway, Yo-Yo Ma. These names are almost predominantly what?
Motorcycles.
Asian! Asian, right? Chinese, Japanese, Korean, right? They didn't know about Western music until the early 1900s. Late 1800s, early 1900s. Japan famously was so isolated by their choice that they didn't let dignitaries in until like 1901 or 2 or something like that, where the first sort of outsiders were allowed to come and do a cultural exchange. And so what did we send? We send the New York Philharmonic as part of this big cultural exchange, right? Japan's opening its doors, right? We send the New York Philharmonic. The New York Philharmonic sets up in an auditorium in Tokyo. And what do? They do all their normal pomp and circumstance. First violinist comes out, points at the oboist stands up, plays A440. The rest of the, and if you've never heard an orchestra tune, it sounds terrible, right? Everybody's trying to find their notes and nobody can hear what's going on. Okay, right? And there's squeaking and honking coming from the clarinets and all kinds of stuff going on, right? What did the Japanese people do?
Leave.
No. Gave them a standing ovation. As soon as the tuning was done, before the conductor ever walked out, all the Japanese people were on their feet going, ah! Because they were told at the beginning of the concert by the person who was emceeing the whole thing, no matter what they play, stand up and clap, because it's what Americans like. And today, some of our greatest instruments and greatest performers come from that culture. They've mastered it. They're so good, right? So, yeah.
Some of the videos you'll see like 10-year-olds playing better than like college students. It's insane.
They're so good. They're so good. They have totally absorbed the Western music and ideology, and they're running with it, and it's fantastic. Take it. You can do a better job than I can. All right, let's get back into the physics of everything that's going on here, okay? When it comes to musical sound. Because your parents might come to you and say something like, turn that noise off! You're like, but boy, that's my music. It's my jam. There is a definition for noise. In science, noise is any sound. This one didn't flip. Why didn't it flip? There we go. Okay? Noise is random. There is no pattern in the waveform for noise. The wavelength and frequencies are changing at random. And so anybody can pick out noise. It sounds like the sound a fan makes. White noise, static, that's true noise. Anything that has a repeating pattern to it, by definition in science, is music. Because our brains, and this transcends culture, they know when they hear a musical sound. Parts of our brains light up. Everybody will agree it's music as opposed to noise. You may not like it. It might be in a different tonal format than you are culturally expecting. For example, in India, they have 7 and 15 tone scales. There are some Buddhist monks that can sing like 3 notes simultaneously, right? From their vocal cords, from their nose, and from their ears. I don't know. Like, they're amazing, but it sounds like a Buddhist chant. It's very sort of guttural, but it's still musical. Musical forms have this repeatability to them. And every human knows when they hear music. I mean, I like it. That's culture. But they do know when it's music. The difference between, say, a flute and a tuning fork and a clarinet comes down to the particular waveform that the instrument makes. On this screen, you can see a pure sine wave. Those are the tones I was playing for you earlier. They don't sound pleasant at all, do they? You kind of wanted that to go away as fast as possible because it's just that pure tone. It sounds bad. But flutes, clarinets, violins, pianos, all of them have a richer, better sound, and it comes from the complexity of their waveforms. But you can still see that there is wavelength here, right? There is frequency. It's just getting more complicated. And with that complexity comes taste and beauty and whatever, right? These waveforms come from the harmonics that are being produced by the musical instrument. When a piano and a flute play the same A above middle C, 440 hertz, they're playing the same fundamental frequency. The piano and the flute both at A440. The difference is that the flute's harmonics, the fundamental and the successive second, third, fourth, fifth, sixth, all the way up to like the 15th harmonic, are going to be a different pattern than the piano's set of harmonics. Piano will have a set of harmonics up to 30. And when a musical instrument plays a note, it doesn't just sound its fundamental frequency, it sounds all of its harmonic frequencies simultaneously. And when you add together those frequencies into one waveform, you get the complex waveform that you have. These right here, these pictures are called Fourier transforms. And I don't know if you've gotten into any math classes where they maybe mention a Fourier fast transform or a fast Fourier transform. No? Some of you? They might do it in differential equations. Depends on your teacher. This is a mathematical transform that allows you to take a wave that looks very complicated and break it down into the individual harmonics that wave is being produced from. The fast Fourier transform is a computer version of it that lets the transform happen very quickly. This is the transfer. This is the mathematics that has made like noise canceling headphones possible, right? The ability to do these Fourier transforms has revolutionized medicine, economics, all these different kinds of things. Being able to pull out how strong is a harmonic of this repeated pattern. Very powerful thing. But as you can see here, clarinet, right, has got more stronger harmonics and more of them than the flute does here. So the flute's going to sound closer to the purer tone, whereas the clarinet's going to sound more rich or something, right? So it's these harmonics that are really driving it. Again, we've talked about how these harmonics form on a standing wave, and we've shown you, like, here's the first, here's the second, here's the third. The truth is that when a musical instrument is played or when a string is doing what it's doing, even yesterday in lab, okay, all the harmonics can be present. In lab, we were making sure that you could only see one. Only a couple of your groups were getting a little of a peek behind the curtain because sometimes you would see your thing shift. The frequency would stay the same, but it would like sort of shift this pattern. It was trying to find the fundamental and vibrate at the same time as that harmonic was going on. So when a violin player bows their instrument, okay, they're causing that string to vibrate. It vibrates at the fundamental and all the other harmonics. And those harmonics are determined by the materials the violin is made out of, the shape that the violin is made out of, and whether or not that sound is coupling well between the instrument and the traveling wave that is produced. Because you've got standing waves on the instrument, and those standing waves causing vibration of air molecules will then push that sound out into the audience. Why are violins shaped the way they are? Because that's the shape that was decided on over many centuries by artisans and craftsmen who were engineering for a specific sound and to amplify that sound. If you take a string and you just bow it in the middle of the air, it doesn't sound very good at all. When you attach it to the wooden body of that violin in that specific shape with those holes and all that sort of stuff, it becomes a different sound. Because the strings are causing resonance in the body, which causes standing waves to happen, which causes harmonics to happen, and then all those are transmitted to you, and you go, oh, sound. Music. I talked about the closed pipe, right? And the difference, right, between open and closed pipe. And what happens in the closed pipe? What happens to the odd harmonics? They go away, okay? So here's a video. It's not a great one, but it's free, royalty free. So here's a trumpet instructor, and they have a mute in the end of the trumpet here. It's like a plug that goes in to the end of the trumpet.
Let's talk a little about trumpet mutes. A mute is an appliance that you put in the bell that changes the sound of the instrument. Open or without a mute, the trumpet sounds like this. Sometimes composers will write for a different color for the instrument, and you get these by taking a mute, just like this, and putting it inside the bell of your horn, twisting it slightly so that it stays and doesn't fall out. That's very embarrassing. And this will change the color of the sound. This happens to be a Harman mute, and this one sounds like this.
So, number one, it sounds quieter because you can't get as much amplitude coming out the end of the instrument. But more importantly, it sounds different. How would you characterize the sound with the mute in versus the mute out? Thinner? Flatter? I've heard the term muddy. You use to describe the sound that comes out of a trumpet like this. It's got its mute installed. Okay. In jazz, they would say it's sexy. Because a lot of trumpets in jazz are that more muted tone. Okay. By putting that mute in the end, they have formed an almost closed pipe. If it was a closed pipe, we wouldn't be able to hear anything, right? So some sound has to come out. But by putting that mute in, it's a closed pipe. The closed end is the muted end. Where's the opened end? It's where the mouthpiece is. How's that an open end? Isn't it sealed? Yeah, what are the lips doing inside there? Okay? That's what you do when you play a trumpet. Right? All day long. That's an antinode. That's an area where air molecules are moving a lot. So even though it's like sealed, right? You have to have the right embouchure and all that kind of stuff, right? It's still an antinode. And the mute is the node end. And so you're cutting out all of the odd harmonics. And it changes the nature of the instrument. In medieval Europe, if you were in with the king, right, you might have a church built on your fiefdom or whatever, maybe even a cathedral, and there would be these beautiful pipe organs in them. Just some of the most incredible musical instruments we as human beings have ever made. Large, mechanical, breathing instruments, okay? But if you were not in with your Lord and you lived in a serfdom and maybe your church was a mud hole in the ground somewhere, you would be called a pauper. Again, I'm not responsible for the English spelling of these words. Anybody know what this word means? It means poor. Okay? It's a polite term for a serf who is in fact a slave, right? But paupers were poor people. And so in your church, you may not have money for the organ or anything, right? So you might have a pauper's organ. Pauper's organs, very few of them exist today because the pipes, instead of being made out of metal, were usually made out of wood. And they were made with closed pipes, not open ones. Why closed? How long does a closed pipe have to be compared to the same note in an open pipe? Half as long. An open pipe is V over 2L. A closed pipe is V over 4L. That's half the length right there. So you can get the same notes out of a closed pipe with half the material as an open pipe. And so if you're poor and you can't afford longer pipes, what do? You make shorter pipes. And that's why you would have a pauper's organ that sounded money. It didn't sound bright the way that organs usually do.
So, on instruments where, you use your fingers to, do all that.
Yeah.
When you're playing the deeper notes, you're closing more.
Making it longer.
Exactly. So making it longer.
Yeah. Wherever the hole opening is, sets the length of the standing wave inside of that instrument. And anybody that's played clarinet like me knows that you have to kill a lot of ducks before you can finally get that standing in. Not literally. When you play wrong on a reeded instrument, it sounds like they're slaughtering waterfowl.
I play saxophone. It sounds more like a goose.
Goose. Yeah, it depends on, is it a bass, alto sax, right? Okay, before I let you go, you can do standing waves in 2 dimensions. It can be difficult to see. Fair warning, flashing lights, because they're going to use a strobe light in this video.
Have you ever wondered how the head of a drum vibrates when it is struck? We'll use this flexible rubber diaphragm and this speaker to show some of the forms of vibration. The speaker drives the rubber drum head with sound waves from the knee. Here is the fundamental vibration of the drum head seen with a strobe light to slow down the motion.
See the whole thing going up and down?
Here is an oscillation at a higher frequency. Notice the circular nodal line.
Big antenna in the middle, antenna on the outside, but a nodal.
Here is a different type of oscillation with a nodal line running across the diameter.
So in a pipe or on a string, it's a one-dimensional structure. The standing wave exists in a second dimension. On a 2-dimensional surface, what is the standing wave? Where does the standing wave express itself? In the 3rd dimension. So instead of nodal points, we have nodal lines, because we've added this extra dimension.
The frequency is set as shown by the inset at the lower left.
This is a plate that's being driven,
poured onto the plate.
and then they pour sand on it.
Sand illustrates the standing wave pattern by gathering along the nodal lines.
The sand doesn't want to be where the antinodes are. It wants to be where the surface of the
Now
plate
the
is not
frequency
moving.
is adjusted to show various standing waves in the plate.
Change the frequency, and you change the standing wave pattern. 2-dimensional standing waves, where the surface of that plate is bouncing in the 3rd dimension for the antinodes. If you look really closely, you can see some of the grains of sand sort of jumping around as they try to get into the nodal lines. Every frequency, a different standing wave pattern.
The wooden plates on a violin would exhibit this type of oscillation.
So does the shape of the instrument change the way it sounds? You betcha. Yeah.
So the lines of sand, that's the notes?
Those are where the nodes are. In And it's nodal lines, not nodal points, right? It's one-dimensional structures that form the nodes. That was the end of the first unit. What are we doing on Monday? For the exam that takes place on? If I don't see you in class, we'll see you Monday.
Do you think that the pyramids were built like this?
I think they were built on the backs of slaves.